So -1.
Again, hi. Welcome to 234, Math 234 specifically.
I am still your host, Steve Dragoo. A couple of announcements before we get started today. First, I think this class should have been able to see, I've changed around my office hours a bit. Uh, Basically, it took too long to get from here to my office, so I have to start at 12 instead of at 11:30, which is a bit aggressive, considering how far away from everything we are out here. So I'm starting a little bit later after class. And then also I added a Tuesday time. I forget exactly when, but there's an announcement on D2L. You should be able to see it. Go there. Or just look on the instructor page because all of our office hours are there. Second, I will not be here Friday of this week, so one of the other lecturers is going to take my spot. So it'll be Professor Ovenhouse. Uh, he'll go over, I think that's parameterization of surfaces. And then I'll be back on Monday. But I'll still be here this Wednesday. It's the very next section, very next class. I'm still here, and it's after that. I'm out. Cool. That said, we're starting chapter 14 today. So let's jump into it. This one's a bit of a double set, so we might be going quickly through some of the first few problems in order to get to the exciting stuff down at the end. So first, we're going to define a multivariable function. Since this is multivariable calculus, we need multivariable functions first. So we're going to define our functions to be z is a function of x and y. It's going to be two variables are independent variables with just one dependent variable. So think of it like y equals f of x from basically every other math class you've seen. Now it's z equals f of x and y. And if we're doing, a function in particular, that's one input pair maps to exactly one output. So functions do need to pass something similar to the vertical line test, which is why if I want to look at this function here, f of x is square root of 16 minus x squared minus y squared, that thing has the equation of a sphere if I square it back out. It's a sphere centered at the origin with a radius of 4. But in order to be a function, it needs, it needs to be only the top half or only the bottom half of the sphere. Here we'll define top and bottom half based on the higher z values and the lower z values. So z is our determining factor for something's a function, traditionally, anyway. So yeah, multivariable functions. Uh, we start by kind of looking at level curves of a function. It's going to be similar to a topographical map that has contour lines drawn in. In fact, contour lines are another name for level curves. So here I've done my best to kind of sketch out what some of these level curves would look like and how they would translate into the actual shape. So using some bits of color over here. And I just realized that all of my z values on the right are wrong. So let me fix those real quick. Looks like I used copy and paste a little bit too judiciously. So if we're using values of k for 1/9, 1/4, 1/4, and 9, really this should be 1/9 and then 1/4 and then 1 and then 4 and then 9. There we go. I was using that color. So when we're using these level curves, we're setting z just equal to some number, setting our function equal to that number and graphing out what it looks like. Starting with a plot on just the xy plane. To just figure out what the level curves look like, or sort of a cross section of our three-dimensional graph. And then moving over to the right, trying to graph that thing in 3D, I can see that this thing is Well, if I've got 1 over x squared plus y squared, 0, 0 is going to be a point that I'm not allowed to plug in. Or in particular, I'm going to end up with some kind of an asymptote along the z-axis. So I've got sort of a Towers of Hanoi looking thing going on right there. For a computer-generated image, this one over on the right side of the notes, it's pretty similar to what we're looking at. With the exception of this is more of a dome shape, and our graph should have some asymptotic behavior right in the center. And again, we want to be comparing these things to level curves if we're looking at just the 2D plot. If I've got like a topographical map, those level curves show all of the areas on that geography where the elevation is the same. So where there's a constant elevation, we just kind of trace a little ring around that spot. So here's where we get into the in-class part. And I'll have done some of these examples out beforehand. Well, I'll fill in a little bit of detail, but again, we have kind of a dense lecture today. So I'm going to move somewhat quickly through these and then come back if there's time. So we want to look at the domains and ranges of multivariable functions. Since our domain is now going to contain 2 variables, so usually it's got an ordered pair, so an x and a y value is our input into a multivariable function. Our domain isn't just going to be an interval anymore. Our domain needs to be some sort of region, so like a 2-dimensional kind of a region. Because again, there needs to be both a set of x values and a set of y values. Our range, however, is going to still be an interval like we're used to, because our multivariable function takes 2 inputs, again being both x and y, but its output is just going to be a single real number. So our range will be just like we're used to from algebra. We'll still express it in interval notation, though it will require a little bit of extra working. But the domain is going to be the new and exciting one, where it's a lot easier to understand a domain if we just graph it. And at least for this first example, there wasn't a whole lot of excitement going on. I basically just found that there were 2 sets of values that x and y couldn't be. Since I am dividing this thing by both y minus x and y minus x cubed, I need to make sure that those 2 factors are not equal to 0. And then outside of that, I can plug in any other ordered pair I like into this function. So as long as I'm not on either one of those 2 red lines, the whole rest of the real number plane is going to be fine. And if I just do a quick review from algebra, 3 simple rules for domaining my multivariable function. They're on screen. Don't divide by 0. Don't take the square root of a negative number or an even root of a negative number. And don't take the log of a non-positive number. And so for the most part, we'll stick with those 3 restrictions for domains. If we do look at any inverse trig functions, there might be some extra rules that we have to add in for those too. But for the easy ones from algebra, don't divide by 0, don't take the square root of a negative number, and don't take the log of a negative number or 0. And so we'll use those rules to try to find some domains. So let's work through an example. So considering the function, the natural log of x squared plus y squared minus 1 over x, sketch the domain and write it in set notation. To save time, I already sketched out what the domain should look like. I'm just going to justify why that picture is the correct one. So for starters, I need to look at the inside of my logarithm, which is x squared plus y squared minus 1. And I need that chunk to be greater than 0. So that's one of my 3 rules. If I've got a logarithm, I need to make sure whatever's on the inside is a positive number. And I also have a denominator, so I need to make sure that that denominator is not equal to 0. I'll solve the inequality on the left. X squared plus y squared should be greater than 1. And then that's where I ended up with my sketch on the right side. If x squared plus y squared is greater than 1, I need all of the area that is outside of that circle. And not including the circle itself. So I drew it in red to be like a, don't include this part. Additionally, I need to not be along the line x equals 0, which is the vertical line, the y-axis right there. So both of those two lines are going to be excluded from our domain. And then also all of the area that's on the interior of the circle. So if I were to write this in set notation, I would say that the domain are all ordered pairs x and y such that x squared plus y squared is greater than 1 and x is not equal to 0. For the most part, I think when we're looking at domains, we'll be relying a lot more on their sketches than on their set notation. All right, another one. Considering the function, the square root of y minus x, find the domain. Well, if I have the inside of a square root, if I have a square root in my function, I should just make sure that the inside of that square root is greater than 0, greater than or equal to 0. Which means y is greater than or equal to x. So I can just add that x over. Translating that into a graph, that looks like all of the area that is above the line y equals x. But this time I also want to include my boundary line as well. And to illustrate that, I sketched it in green. I know that when we look at a web work problem in a minute, they'll be using dotted lines versus solid lines to indicate whether a boundary is included in the set or not. But I was using green and red. So if I want to write that in set notation, again, that'll be the set of all pairs x and y such that y is greater than or equal to x. Again, I think the sketch tells us a lot more than the set notation does. All right, then finding ranges of these things. We'll talk about it in this example. It's all worked out, but I just think that this example ended up being a little bit too simple, so it's hard to sort of see what's actually going on there. So we're going to work out a secondary problem in a moment. But if I want to identify the range of one of these multivariable functions, first think about whatever base function you have and go find its domain just from algebra. Don't apply any of the new calculus stuff we've learned yet. Just head back to your algebra knowledge, get the range of your function to start, and then worry about adding restrictions into that based on the function that we have. Whether that be a series of linear transformations or some kind of a domain issue, because now that we're adding in these multivariable functions, some different things might be happening. So for this particular example, my base function is the square root of t. I just have a square root function, and I know its range is 0 to infinity, including 0. And the inside of our actual square root, the one that we have in our multivariable function, is y minus x. So we don't have any values. There are no real numbers we can't hit on the inside of that square root. Right, as long as our inside is positive, which we've already made sure that we have, we won't need to run into any other restrictions. So the range of our function, square root of y minus x, is the same as the base function of 0 to infinity. Again, not a lot exciting happened, so it's a little difficult to see some of the nuance to these problems. So I want to go add in a second example. But first, some level curves, and then trying to sketch out what our graph looks like. Again, I took the liberty of doing this ahead of time. This ended up being a bit of an intensive process. If I want to know what the level curves look like, I should just set z equal to k, or set the other side of my function equal to k, and start working with the problem until it ends up in a form that I recognize. In particular, if I square both sides, and then move my x term around, I end up with the equation y equals x plus k squared. Remember, the k is just a constant value, so I'm just going to rewrite k squared to be b, because it makes things look a little bit nicer. Again, it's a constant either way. But if I just have the equation y equals x plus b, I know that's going to be a series of lines. And in particular, if I pick numbers like 0, 1, 4, and 9 to be adding to x, so for my intercepts, I get the lines shown on the left, and then I sketch those out over on the right. Because it's for whatever that k value is. If I solve each of those numbers, 0, 1, 4, and 9, back for the original k, I know that those are going to be my z values, which is why I've taken the square root of those numbers over on the right side. So a z value of 0, 1, 2, and 3 corresponds to the b, or the intercept values, of 0, 1, 4, and 9. And then I can just kind of follow those lines along as they go. And I can also see that there is a square root function that should show up somewhere in the sketch. I just have to look at it from the correct direction. I can see here on the left and the right sides is where I see that square root function showing up. But enough on that. Let's go look at another problem. So I pulled this one out of the homework. This is homework set 10 in the very first problem. So considering the function natural log of 16 minus 16x squared minus y squared, find its domain. And here we're going to be choosing from 4 options. But what I want to do is look at the inside, because again, I only have a few rules for these functions. In particular, on this one, I need 16 minus 16x squared minus y squared to be greater than 0. Rearranging that to give me an equation that I kind of recognize, I get 16x squared plus y squared should be less than 16. And that looks kind of like a circle, but really it's an ellipse because I've got an extra figure stuck on my 16x squared. So if I go take a look at the available options, in fact, I've taken the liberty again of writing out what each of these domains are representing, because there is the same ellipse that shows up in each of the 4 options. Those ellipses are 16x squared plus y squared equals 16. But then based on the shading, each one represents a slight variation on what the domain could be, as seen drawn out here. So on the web work, they'll be using a solid line, like that dark blue line that goes around the edge to indicate that I'm including the barrier. So you can see for the 2 on the left, I have a greater than or equal to 16 and a less than or equal to 16. Whereas on the right, just a strict inequality, strictly greater than and strictly less than. But I needed to be strictly less than 16, so D is going to be my best option here. And then the range of this thing. Well, I want to start by looking at the range of my base function, which in our case, that base function was the natural log of t. Which has a range of 0 up to infinity. No, that's not true at all. That's its domain. The range of a natural log function is all real numbers. Ugh, I knew that. Right, I have to stick a positive number into a logarithm, but I can get any real number out. So now I should add in the restrictions. This is step one, was figuring out the range of my base function. It's all real numbers. Step two was adding in any restrictions as needed, which is where we should come back to our interior bit. We had 16 minus 16 x squared minus y squared. Right, that was our inside bit. And I know that the domain of one of these logarithms should be 0 to infinity, which we already had looked at, but our particular interior function, we have a rather restricted domain, right? We can only get points that are on the inside of that ellipse, which means we have a maximum value here. At 16. Right? Our domain, our input collection of numbers cannot be bigger than 16. That was its maximum. That's its largest, the largest element that I can hit. And that maximum specifically will occur at 0, 0. At 0, 0. All right, if I plug in 0, 0 for x and for y, I'll get 16 minus 0 minus 0, which is 16. So if I think about how that's going to impact my range, well, I can still get as far negative in this natural log function as I'd like to, because I can just get really, really close to that border of the ellipse. Any point near that border is going to spit out a very large negative logarithm. But if I wanted to look at a maximum value, I can't get bigger than 16. So the range of f of xy, which again was the natural log of 16 minus 16x squared minus y squared, is going to be negative infinity up to the natural log of 16. And this time I'm going to include the natural log of 16 in my range. So I'm going to have a bracket there. Since the point 0, 0 is included into the domain, I can plug that in and get a value. So when it comes to adding restrictions in from our domain, you just have to think about how our restricted domain might impact the function it's being plugged into. Usually that means looking for some maximum value or some minimum value for the input function. Cool. Then let's go look at another one. So considering the function 3 equals 2 to the x plus y, find its range. Also notice here that, oh wait, sorry, this one's x times y. I think the next one's x plus y. Notice I don't have any restrictions on my domain because I don't have any of the functions that I would need to worry about. Right, I don't have any denominators, I don't have any square roots, I don't have any logarithms. So I can plug in whatever I want for x and y. So run through my process. Step number 1, finding the range of the base function. Here, I want the range of 2 to the t power. That's my base function. And I know that exponentials have a range that are just the positive numbers. Right. I can plug in whatever I want for my exponent, but 2 to any power is always going to be positive and not 0. So it's got a range of 0 to infinity. So then step 2, I want to look at the range of 3 plus 2 to the t. Since my function has a linear transformation on it, I'm shifting the whole thing up by 3. Which means I should have a range of 3 up to positive infinity. And then if I add in any domain restrictions, which I have none of, that means the range of our function here, range of 3 plus 2 to the x times y, is just 3 to infinity. So sometimes our new ranges come from just linearly transforming whatever base function we started with. In this case, we have a linear transformation of up 3. Other times it'll come from restrictions on the domain. I'm sure you'll get used to it as you work through homework set 10. All right, and for the last one in this set, which of the following best describes the level curves of e to the x plus y? So, quick word of warning on the level curves. They often don't look anything like the function that you start with. Right, so I've got this multivariable function that's e to the x plus y. It will be some shape in 3 space. But if I'm going to look at the level curves, I'm just looking at cross sections of this surface that are parallel to the xy plane. So oftentimes level curves will end up looking almost nothing like the original function, or at least not what you'd expect looking at the original function. But the way to find these level curves is to just replace z with k. And then just solve the equation probably for y, or at least get it down to some form that you would recognize. So if I start working on that, I'll take the natural log of both sides. Sorry if sometimes my natural logs look like h's. I've been working on fixing that, but it just never takes. So I'll just take the log of both sides, have natural log of k equals x plus y, solve that thing over for y to get y equals, no, it'll be negative x plus the natural log of k. But remember that k is just a constant. So don't get tripped up by the natural log that's on there. The natural log of k is just a number. And maybe to emphasize that point, I could just replace k or natural log k with a plus c. Right? Because either way, those two things are just numbers. So sometimes it's helpful to replace some of the constant terms that you're collecting with just one single letter, one single constraint parameter, to sort of show off what that value is. Because I think looking at it that way, it's pretty clear to see that these things are lines. These level curves are going to come out to be lines. So that's our quick crash course in the introduction to multivariable functions. We're also going to add in partial derivatives. All right, so here we go. A partial derivative of f with respect to x at AB is denoted by f sub x of AB. So we're going to just use those little subscripts to represent our partial derivatives. effectively what a partial derivative is it's just taking a derivative of a multivariable function with respect to only one variable at a time. So if my function is x squared y plus sine of xy, and I want the x partial or the partial derivative with respect to x, I'm just going to treat y like it's a constant and then just take a derivative. So you can see here in the example that I've worked out, I've got 2xy plus cosine of xy times y, because that's what I'd get from my chain rule. Right, so just pretend y is a constant and take a derivative of that function as if it's just a function of x. If I do the same thing for the y partial, okay, same function, different partial derivatives, time with respect to y instead of with x, but I'll use the same idea, just treat x as if it were a constant. And I get the derivative that you see right there. Technically, these things are defined as a limit, which is the same derivative limit that you saw from all the way back in Calc 1. We're going to take the limit as h goes to 0 of the difference quotient. Basically look at taking 2 points that are really, really close together and finding the slope that's between them, and then make the distance between them go to 0. Which means we need to talk about multivariable limits, and these get wild real fast. So we're mostly just going to gloss over section 14.2. You won't need a ton out of this set. But the main difference between a multivariable limit function or a multivariable function limit and the limits that we're already used to is that previously, when we did limits, we just had to check the left and the right side and confirm with the two sides of the limit agree with each other. So then the formal limit, the main limit that we looked at, is really just a two-sided limit, one from the left and one from the right. But with a multivariable function, we don't exactly have a left and right anymore. We have more of an omnidirectional limit that we have to look at. Which means that finding the limits is a bit more, well, but practically you just kind of get a little more loose with it. If I'm trying to show that a limit does not exist, I just have to find any two paths that converge to the limit but go to different values. So in particular with this set here, I took two different paths to look at the limit of this particular function. One where I came in along the line x equals 0, one where I came in along the line y equals 0, and I got totally different numbers. In fact, if I take any linear approach, that approach is going to depend on the slope of the line that I come in with. And because those values don't agree with each other, the limit isn't going to exist. Whereas if a limit does exist, I would just try to solve it out algebraically and then go from there. Again, don't worry too much about limits. We aren't going to do a ton with them. But partial derivatives we're going to do a lot with. In fact, that kind of is what we're doing from here until the cows come home. So back to our definitions of partial derivatives, there are a few different notations that come up from time to time. I put them in this box. The most common of which are just f sub x and f sub y. Then if we go to look at second order partial derivatives, which are just a second derivative, but now we're gonna, get fun with them. There are 4 potential second order partial derivatives. Instead of back in Calc 1 where we would have just had a single second order derivative or a single second derivative. When we do partial derivatives, there are 4 of them. So there's the 2 straight second derivatives. So f partial x and f partial y. Right, so just do an x derivative twice or do a y derivative twice. Those give us sort of the pure second order partial derivatives. But we also have the 2 mixed second order partial derivatives. So fxy and fyx. And because we want to be extra complicated and introduce lots and lots of notation, I want to point out that when we use subscript notation versus the partial derivative notation, the order in which we read reverses. So if we're looking at the subscript notation and I see f sub xy, that means x partial first, y partial second. But if we're reading the partial derivative notation or the partial notation, these things are really nested on the inside of parentheses. So we have to read inside out, which effectively means we're reading right to left instead of left to right. However, most of the time it doesn't matter. So there's this guy named Clairaut. He has a really fancy theorem that says that as long as you have a nice function, the mixed second order partials are equivalent to each other. So most of the time, f sub xy is going to be equal to f sub yx. So as long as our function is nice enough. Now, what do we need for a function to be nice enough? We just need our partial derivatives to be both continue. No, just continue. No. We just need our partial derivatives to be continuous and defined around our plane. Again, we'll just use the hand wavy explanation that as long as the function's nice enough, the mixed second order partials will be the same in either direction. Pretty much everything we're going to look at is going to follow Clairaut's theorem. So just to highlight that real quick, I went through and actually took these two mixed second order partial derivatives in each direction. And I got the same thing both times. So I have a nice function here. You can see that nice function can be sort of a relative term. But all right, let's go actually do some of these. So considering our function, v is xy over x minus y. Let's take some partial derivatives. For starters, I'm going to rewrite my function to be xy times x minus y to the negative 1. So that I can use the product rule instead of going with the quotient rule. So if I take derivatives here, I have a product. Right, I get to treat y like it's a constant because I'm only doing an x partial. So I have xy times x minus y to the negative 1. So I am going to take those partial derivatives. Now, the product rule says that I should first take the derivative of function number 1 while leaving function number 2 alone. So that's y times x minus y to the negative 1 plus take the derivatives the other way. So this will be xy times x minus y to the negative 2, but bring down that negative 1, so it changed to a minus xy times x minus y to the negative 2 times 1. And that would be a perfectly acceptable answer for my x partial. Now, because I need to take more derivatives along this line, I need to get both the straight second x partial and the mixed second order partial. I'm going to clean my function up a little bit. So in particular, I'm going to factor out a y and an x minus y to the negative 2. That'll leave me with some stuff on the inside. In particular, I think this will be an x minus y minus x. All right, if I pull an x minus y to the negative 2 out of x minus y to the negative 1, there will be one x minus y, positive 1 left over. So that, again, could simplify. Since that inside is just negative y, I'll call it negative y squared times x minus y, x minus y to the negative 2. And then my straight second x partial derivative is going to be a lot nicer now. So vxx is, well, y squared is now just a function of y, which means I get to treat it like it's a constant right now. This only has one x factor in it. So I no longer need my product rule. I just need to bring down a negative 2. So this will become 2y squared times x minus y to the negative 3 times 1. Yeah. Cool, and that's my second x partial. To get the mixed second order partial, bxy, go back to bx, but this time take a y partial. And again, I'll need the chain rule. So this looks like it's going to be negative 2y times x minus y to the negative 2 plus the next derivative down the line. This looks like it'll be plus 2y squared. So I'll bring down the negative 2 times x minus y to the negative 3. And then the chain rule says I need to multiply by negative 1. And since I'm not taking another derivative, I'm just going to leave that function as it is, rather than trying to simplify it again. Pause there for just a second. All right, and then let's take a look at the multivariable function that's defined with all three variables, all of x, y, and z. And I want to find the third order partial derivative, f partial x partial y partial z of that thing. So first thing I'm going to do is take a look over at the function that I have and see it's kind of scary looking at first glance. But if I'm going to use that fancy theorem that we talked about that says that I can, any of the mixed order partial derivatives are going to be equal to each other as long as I'm taking the same partials. It doesn't matter the order that I go in, which means I am going to take the z partial first because I'm allowed to go in whatever order I want to. And if I look at this function, that whole second term has no dependency on z. So I'm going to do the z partial first. So this will be x times y plus 0. All right, so treat x and y as if they're both constants and just take the derivative of the z functions. So the derivative of x, y, z is just xy times 1. Derivative of z would be 1. And the derivative of a constant is 0. So that whole thing worked out rather nice. So then go do the next derivative. I don't really think it matters from here. So I'll just do x next. Take a derivative of xy with respect to x, and I get just y. So then lastly, I'll do a derivative of x, y, z, or f partial x, partial y, partial z, and get just 1. So it is worth considering which derivative you want to start with, which partial derivative you want to start with if you're given a choice. Often there's an easy way and a couple of hard ways. Cool. All right. So what do these derivatives mean? Well, each of our partial derivatives tells us broadly how the function is changing in whatever direction I'm taking my partial with respect to. So the x partial roughly tells me how the function is changing if I just look along a direction parallel to the y-axis. Right? Yeah, it's just how is this function changing in the x direction? So if I look at my x partial, just consider taking the line y equals b. Again, I'll be looking parallel to the y-axis. That's the direction the x changes. And just look at the partial derivative of the single variable function. So just reduce our multivariable function back down to a function of only x by plugging in b, and then seeing what that looks like. So again, if I took one step in the positive x direction, then f would change by roughly the f partial x at 8. We're really going to be building these ideas in an argument about tangent planes. Because if we think back to how the original derivative worked, it was the slope of a tangent line. So these partial derivatives are kind of like the slope of a tangent plane. And I'm going to go with slope in a lot of air brackets, air quotes here, because slopes don't or planes don't exactly have slopes, but we can kind of pretend like they do. In particular, these partial derivatives give us the x direction slope and the y direction slope. So to kind of emphasize that with an example, suppose you're surrounded by bees, given this bee density function, right? Tells you how many bees are surrounding you. In particular, this one is saying that there are like 100 bees per square unit, like right where you're currently standing. And then if you move through space, if you move in either an x or a y direction, the number of bees around you is going to change. So currently standing at the point 1, 1, I want to know which of the 4 directions it would be best to run in, either straight left or right, or straight up or down. So what that's asking me to figure out is my x partial and my y partial, and then evaluating it at the point 1, 1. So my x partial looks like negative 2x. So my x partial at the point 1, 1 is negative 2. I'll do the same thing for my y partial, which is 2y plus 3. And then again, evaluate that at the point 1, 1, which is where I'm currently standing. And I get 5. Now, good enough. So these two partial derivatives tell me specifically if I'm moving only in an x or a y direction, what will the change in the number of bees I'm surrounded like look like, right? If you're surrounded by bees, you probably don't want to be surrounded by bees. So the best outcome here is that we run to a place that has the fewest bees in it, roughly construed. So I want the biggest negative change that I can get, which means running in the negative j direction. Negative j is best. So if I were to look at each of those directions in kind, I, j, and negative j. If I run in the positive x direction, I will run away from 2 bees. If I run in the negative x direction, I will probably be surrounded by 2 more bees. If I run in the positive y direction, I'll be surrounded by 5 more bees. But if I run in the negative x direction, I will lose 5 bees. And again, I'm looking to get away from as many bees as possible, so I want the largest negative slope here. And lastly, since I know we are basically out of time, let me just skip ahead to the last example that I've already got worked out. That was too far. All right, the last page on here. The Laplace equation. Which if you're just coming out of like Calc BC, then that name probably doesn't carry a lot of weight. But if you've been through a few engineering courses or possibly some physics classes, the hair on the back of your neck might have just stood up at the word Laplace equation. You'll see more of this when you look at differential equations. We aren't going to do a ton with it here. However, the Laplace equation is one where the two straight second order partial derivatives added together are zero. And we call solutions to this equation harmonic functions. And they can be used to describe things like conduction, liquid flow, or heat conduction, liquid flow, and electric potential. So again, you see it a lot in physics and engineering. In particular, there's the wave equation, which is if I have some function that is some quantity that is a function of both time and space, I can set the second order time partial derivative equal to the second order space partial derivative and find solutions. Generally, what those things look like are trig functions. Right? You hear the word harmonic function, you're probably thinking about sine and cosine, since those two things are harmonic. So we often see solutions along the lines of sine or cosine. The rest of the work is there. I will post it to our class notes right after this. And with that, we're done. Okay, bye, 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 bye.